So let's look at Newton's third law. And a good practice problem with this is, so let's say we have a 6 Newton force and we're pushing on two gliders that are going along a track. And there's a spring in between these two gliders and it is being compressed. And so the spring exerts force back onto the gliders as they move along. And we want to figure out what is the force from the spring exerted on glider A and on glider B. So to really start to solve this, you want to keep in mind the equation force equals mass times acceleration. And this is really the only equation we need to solve this problem, but we're going to apply it in different ways. So the first thing we want to do is we want to set this up to figure out what is the acceleration of the system. The acceleration of the system has to imply all of the masses. So if I rearrange this, I get acceleration equals force over mass. And let's apply this to this actual problem here. So instead of writing force, I'm going to say it's a normal force from the push, from that 6 newtons of force. And it's divided by the total mass of the system. So the total mass of the system is the mass from block A, plus the mass from block B, plus the mass of the spring. So that's the total mass of the system. Now that we have an equation for acceleration, we can look at the force diagrams of each of the individual gliders. So for part A, we want to figure out how much is the spring force exerted on glider A. So we're going to look at the force diagram just on A. So I have a vertical force from the ground, so it's a normal force from the ground or the table, whatever it's sitting on, so we'll just call it T for table. I have a vertical force down from gravity, and those two are equal and opposite because it's not moving in the vertical direction. So we actually don't really care about it, but I like to draw them to remember that they're there. And we have a normal force from the push, that's the 6 newtons, and then we have some force counteracting that, and that is a force from the spring. So that's the spring force exerted on A. It's actually also a normal force because it's pushing back on it, but for simplicity's sake, we're going to call it S sub A. And we want to figure out what this force is, S sub A. So we're going to use the same context that F equals ma, but we're going to expand on it a little and say F net equals ma, and this is acceleration here. And I'm going to take it one step further to say F net of A. Just the net forces on the glider of on glider A are then equal to the mass of glider A times the acceleration. And that's an important distinction. It's no longer the mass of the system, it's the mass of A. And this F net is just, again, we just care about the horizontal components, is going to be the normal force from the push minus the spring force of A, because direction here matters. And that is equal to the mass of A times acceleration. So we just solve this because this is what we're looking for. So SA equals the normal force from the push minus the mass of A. And instead of writing acceleration, because we found out what the equation for acceleration was, I'm going to the normal force from the push over the mass of A plus the mass of B plus the mass of the spring. I can calculate this, so I plug it all in my calculator. I get 6.0 newtons minus, everything should be in kilograms, not grams. So this is 0.4 kilograms. And that's 6.0 newtons divided by 0.4 kilograms plus 0.6 kilograms plus 0.2 kilograms, running out of space. And I should get that it is 4 newtons. We're going to follow the same process for glider B. We're going to start by drawing its force diagram. So again, it has a normal force due to whatever it's sitting on. Again, we'll just call a table. And it has a force from gravity pulling it down. And again, it is also not moving in the vertical direction. So we just care about its horizontal components. In this case, it only has a force going in one direction, right? It doesn't have anything pushing back on it because it's at the end of our system here. So it just has a force from the spring. And that's it. That's the only thing that's actually touching and pushing on it in the horizontal direction. So the same process applies, F equaling ma. The only force, again, on B is this spring force, and that is equal to the mass of B times acceleration. And then so I can apply my equation for acceleration. Mass of B times the normal force of P over the mass of A plus the mass of B plus the mass of the spring. You kind of get the idea here. If I were to plug in all my numbers, again using kilograms instead of grams, I get that this is 0.6 kilograms times 6 newtons over 0.4 kilograms plus 0.6 kilograms plus 0.2 kilograms. And when I plug it in my calculator, I should get 3 newtons.